I'm going to talk about time-dependent properties of granular media, and this is basically what I've presented also at the GeoMod in September, October, and I've not worked on it so far any further because I just changed institutions and I had to settle in and everything, and I'm now in a different institute. I don't have access to the machine anymore, so everything has slowed down a bit. But yeah, in principle, it's a comparison of several materials that are in use for analog experiments. And the main question behind it is what happens when we have a model, especially in an analog model of a Bayesian inversion, for instance, where you have first the phase of extension. Let me see if I can switch to I will use the mouse. I think I cannot switch to the laser pointer in this program here. So you extend and then you form a series of faults in your sand package or in your granular material that you use for your analog model. And then you invert the model again. So you reuse the old faults that you have created and you create new structures that are reactivations depending on the fault angle that it is in. And it depends also because the material is time dependent, which is often overlooked. It also will have an influence in how long your material sits in the extended phase. So the older the faults are, the less likely they are to be inverted. So it's not only a geometric factor, but also time factor factored into this. And I'm looking into quantifying this amount of healing, and I'm doing this with several kinds of experiments. So as an introduction, I can tell you that granular media have multiple friction coefficients. So you see on the right here a typical Moore-Coulomb curve. So what you do is you put your material under a certain normal stress and then you start shearing it. And in the beginning, you will measure a certain peak in stress, which you can translate into a peak friction coefficient, which is the undisturbed granular material. And over time, this stress will decay to a certain, let's say, equilibrium value, which is valid for shear as it's happening, which we call dynamic friction here in red. And this is a relatively low value, usually quite a lot lower than the peak friction. And then what we do in these tests is we stop the shearing and then we re-shear immediately, or basically we unload and re-shear, and then we measure another slight peak, which is the reactivation friction. And this is the part which reactivates the old fault and doesn't create a new fault every time we shear our material. And this effect, this leads to the localization of the deformation, and this is why we can actually also use sand and other granular materials for analog models to simulate Earth deformation. And analog models such as Bayesian inversion models exploit this effect that you can reactivate a pre-existing shear zone in sand. And however, on several timescales, it's also a rate and time dependent property. So it's not only these three frictional properties, but especially the dynamic friction can be very rate dependent. So the faster you shear, the lower your friction in the granular material is. In analog models, usually this is not a problem because we shear at very low rates. But on the other hand, we have a time dependent effect, which increases the reactivation friction over time. And this is also one of the reasons why I'm doing this study. We have this community-wide benchmark to compare different rate and time dependent properties from many analog materials from the lab, from several labs. So these are quite a lot of labs from the MSL community that are involved here. The plan is to build upon a previous existing benchmark, which looked at these frictional properties that I've just shown. So the peak, dynamic, and reloading friction. And we use old samples that have been used for this benchmark, but I also collected some new samples. And the machine that I'm using is a conventional ring shear tester. So the material is put into this cell down here, and it's rotated from below, and then we measure the shear stress along a lid. And we can also measure the thickness of the granular package and so forth. It's a standard machine to measure granular properties. The testing procedures, we do the standard test that I've just shown you, so we get the Mont Coulomb friction if we don't have it yet. So if there are new samples, there are several like plastic sands which have not been used 20 years ago. So there are quite some, or 10 years ago. So there are quite some new materials that we're also testing. And then we do a slide test to get the healing rate and a velocity stepping test to get the velocity dependence. And now I'm going to show the results and also the methodology of the slide test. So what we do is first we sieve the material similar to our standard procedure in the lab. So we sieve from a height of about 30 centimeters into the cell. Then we apply a normal stress of 1000 Pascal, which is roughly the range that usual analog models are in. And then we pre-shear. So this is the peak that I'm talking about. So in the beginning, we pre-shear the material to have this equilibrium friction, and we have a nice shear zone formed. And then we do several slide cycles. So these cycles are intervals of shearing, and then we hold for a certain amount of time, then we shear again. And these cycles go from 10 seconds to about 10 hours. We do 8 intervals with 3 repetitions. And in the end, we have quite a large database that we can use. And then we pick the apparent friction that we measure. So this is a schematic curve. I will show an experiment curve later. And we see a slight increase of this peak friction for 10 seconds in comparison to 100 seconds. We have a slightly higher increase. And then we pick these values and we get this delta mu in this case. And we plot this against the hold time. And we will see an increase of friction depending on hold time. And yeah, we fit this with a log linear relation, and from this fit we get a power law exponent, which is the healing rate. This is such a time series, so this is just a simple, I think it's a 60-second or 30-second hold or something. So no, it's a 100-second hold, sorry. Yeah, so this is the hold period. So down here you see the loading rate. We hold, we then start shearing, we stop again, and there is some evolution of the stress during the hold. So we also analyze this, but you see this peak here after every reloading phase. We see this strong peak, and then we drop down to the dynamic friction again. And the difference in these peaks between the individual hold intervals, so this is only 100 seconds, but if we can do this for all others, we get these delta. And if we plot this, we can already observe certain differences from sample to sample. So for instance, this is on the left, you see a material that has a very weak healing, so the slope is very low. So after a certain amount of hold time, you only get about 0.5% increase in apparent friction. But other materials like this glass bead sample that we have from the GFZ, it has a much higher healing rate, about 2.5% of frictional increase per second. And plotting all materials together, we see that similar materials are similar in healing, not always, but roughly. So the glass beads from the GFZ down here in purple, they are similar in their frictional sliding, and they are also similar in their healing. Lower grain sizes apparently have a higher healing rate. All the sands are together in their frictional sliding strength, but also there is some spread between the individual healing rates. But we can say that at least sand doesn't have a very high healing, but there are other materials that are commonly used that can have a quite high healing. And what this implies, oh, now I just realized that all the mathematical formatting is gone for this presentation. Let me quickly switch to the PDF where I can be sure that it's there. Screen. Okay. Here. Okay. So if we assume that we have a peak friction of about 0.72, which is the typical value, and a reactivation friction after 10 seconds of about 0.62. So the reactivation of a fault is much easier than actually creating a new fault, and a healing rate of about 2%. Then after 5 minutes, or after a prolonged period of time, so 5 minutes, 1 hour, or 24 hours, we already go into the region where you can actually recreate a new fault instead of reactivate one. So after 1 day of rest, so if you expand your model and you reload the model on the next day because you did something else, then you can encounter different results than if you would reactivate your model within a few seconds or minutes. So this can have quite a strong effect. We also had some models in our lab which reacted differently because some people sit them in on the Friday before they left. It was a normal model, not just not an extension model, but yeah, this can have dramatic differences. And yeah, faults of different age in the model can behave differently in the analog model as well as in nature. Yeah, this is also known that in nature, the older the fault is, the better it is healed if it's not active. And this we can also maybe exploit in our model. So if we create a model that takes into account the healing, then we can wait for a certain amount of time to model an extensional domain that is sitting there for several millions of years instead of one that is sitting there for only 100,000 of years in the same setting. So this would be an application of this yeah, study. And models that rely on the fault reactivation, you have to take into account that your model can be different if you run it with a different time setting. And so you should not let an inversion model sit in the inverted stage for more than a day. And of course, models with pre-existing weaknesses with cutting, and when you change the package density with some mean, you should rerun the model relatively quickly. Otherwise, you get this healing over time and you go back to your initial strength again. Yeah, so that's it from my part. Are there any questions?